So long as there is no airflow, the water levels remain equal, because the atmospheric pressure everywhere is the same. When the wind starts, the air flows through the venturi and over the holes in its surface. As the air flows forward, its pressure sideways becomes much less. The colored water rises in the pressure gauges. The highest level shows where the pressure is most reduced. This is where the gap is narrowest, making the airflow fastest. If we could see the airflow in the venturi, it would look like this. The top half of the venturi is replaced by a flat plate. The air flowing on either side of the flat plate is almost unaffected by it. The remaining half of the venturi now does all the work of narrowing the gap and speeding up the flow, and there is a reduced pressure over its top surface. We can remove the flat plate altogether and see that there is still a reduction in pressure. The air itself, flowing where the flat plate was before, becomes the inactive side of the narrow gap. You've seen the venturi section. Now look at a section of an aeroplane's wing. They're much the same shape. An aeroplane's wing is so shaped that when it's moved forward at a slight angle, the air flows over its top surface at an increased speed, as it would over the lower half of a venturi. A wing section placed in the water flow machine shows the speed up of the particles over the front or leading edge and the topmost part of the wing. This flow reduces pressure on top, and atmospheric pressure underneath lifts up the wing, just as the paper was lifted when the man blew over the top of it. It must be remembered that it is the top of the wing which plays the most important part in flight. It's the increased speed of flow over the top surface which reduces pressure and gives us lift. The underside plays a small part too, as will be shown later in the film. Here is a wing section made like the venturi, with holes in its surface. These can be connected to the pressure gauges to show the pressures on the wing when air passes over and under it. The holes on the top surface are connected to the 4 left-hand pressure gauges. The wind starts. The colored water rises most where airspeed is fastest, that is, at the highest point on the top surface. If we want to reduce the pressure even more on the top surface, we increase the angle of the wing. Increasing the angle of the wing is doing exactly the same as making a narrower gap for the air to go through. This would cause a faster flow and a lower pressure. Put a wing section in the water flow, increase the angle, and you can see the speed up in flow. We can see by the way the liquid has gone up that pressure is less. There are holes on the underside of the wing which can be connected to the 3 right-hand pressure gauges. Since the wing is set at an angle to obtain lift on its top surface, air must strike the underside. This airflow is slowed down, causing an increase of pressure. The water in the right-hand tubes is forced down, showing this increase in pressure on the underside of the wing. With the wing at any normal flying angle, then, not only is the pressure on top reduced because of the speed up of flow, but underneath the wing the pressure increases slightly above normal air pressure because of the slowing down of the flow. It's because the moving wing can change the pressure of the air around it that the aeroplane can fly. This wing section attached to a balance shows how angle can affect the lift, even though the airspeed remains the same. with the wing at 0 degrees, it will lift 2 weights and remain balanced. Increase the angle to 5 degrees, and it will lift 3 weights, because although the main airflow is the same speed, the airflow over the top of the wing has become faster and pressure is more reduced. A further increase in angle to 15 degrees gives greater lift still. So an aeroplane increases its angle when it wants to lift a greater weight, or if it wants to lift the same weight but fly at a slower speed. For example, when landing, the pilot flies his plane as slowly as possible, but he must fly at a large enough angle to give him lift until his wheels touch the ground. Let's see him do it again and stop the picture just before he lands. You can see the large angle between the wing and the direction of flight, giving lift up to the last moment before the wheels touch the ground. At too great an angle, lift begins to fall off. The wing has reached what is called its stalling angle. At this angle, the airflow over its top surface breaks down. Let's put a wing section in the water flow and bring it to the stalling angle. The particles no longer flow smoothly over the wing, but become restless and turbulent, even creeping up the wing from back to front. Here is an aeroplane approaching the stalling angle. As soon as it reaches it, lift decreases, and the aeroplane drops away several hundred feet before it can be brought under control. So an aeroplane flies at any angle less than the stalling angle, according to its speed and load. Lift is the force that supports the weight of the aeroplane. It comes from changes in the air pressure caused by the air flow. The air flow is created by the shape, the angle, and the forward movement of the wings.